Okay, well, thank you. Well, you may be wondering why a seismologist is giving a talk about geodetic data. I've wondered that myself, but perhaps the goal is to demonstrate that if a seismologist can use these data, anybody can. I'll apologize to the geodesists for telling you things you already know, and emphasize that this is really a work in progress, and that I think we've only begun to just explore what some of these high-rate data offer. Acknowledge some of my co-authors, they're listed here, and also Kathleen Hodgkins, who's been very helpful as well. I've listed here the things that I'm going to talk about. First, we spent a lot of time asking ourselves, what is it that we can observe currently about how faults slip from looking at seismic and geodetic data? And we've done that in the context of looking at one of the questions about earthquake, about slip, and how it's the scaling between duration and moment, a slide that Sridhar mentioned earlier. And it provides a context for looking at what it is we can and can't observe. And I think what you'll see is that these high-rate data really offer the possibility of filling in some really key gaps in what we can observe. We've then begun to explore how well these high-rate data really can fill in some of the gaps. And then lastly, a more pragmatic example of how these data can be used in a monitoring sense. So this is now an iconic figure for those people who studied fault slip by Ide and others from 2007. What they did was plot the slip event duration on this axis, and the log of the moment on this axis, and what the observations are shown in the symbols. And what they inferred was that there were two scalings between duration and moment. These are the slow slip scaling, in which moment scales as the duration, and those that go with fast slip or earthquakes. I'll also point out that the coding here, anything that's a geodetic observation is shown with open symbols, and those with solid symbols are seismological. Well, just to illustrate why this scaling question is important, is illustrated, and it's a bit of a digression in the next two slides, and it's really a pretty simple concept. If we take three basic source parameters, the seismic moment, the stress drop, and the length as it relates to the average rupture velocity and duration, we end up with this sort of classic relationship that the moment should scale as the duration cubed. And in fact, that's what the earthquake data show us. So empirically from the previous slide, this is what we find. What that implies is that this constant is independent of the rupture length. Again, it means that the rupture velocity and the stress drop are independent of the earthquake size. However, if we look at these slow slip events, again, we have our fundamental relationship here. What the observations, at least what Ide and others suggested, is that the moment scaled as the duration. Mathematically, this is that statement. And if we compare these two, the only way that this can be true is if that constant depends on this product. That means that the product of the rupture velocity and the stress drop have to scale inversely with the length of the rupture. So very different physics implied for how slip events grow. Okay. So now we're going to return to this question, is what is it that we can really observe, and how does that overprint what we infer from these kinds of observations? So the first question is, what is the recurrence, what kind of imprint does the Earth impose? So what we've taken this slide here, this iconic figure here, and put down what we would observe as shown by these gray dots if we had a uniform distribution of events in duration, but they were distributed according to a Gutenberg-Richter relationship in terms of moments. So basically, as they get larger, we have many fewer events. And you can see some of the effects of that in the seismic data. We have fewer events as we go to larger moments. Well, another thing that affects what we can observe is how long and what kind of measurements we have. This is an old map. These are now all operational. This is the high-rate GPS network that operates in the western U.S. These are now all blue. But I will point out that the processed high-rate data, the high-quality processed data, are only available for particular large earthquakes. So these are not continuous data that are readily available unless you want to process them yourself, which most seismologists I don't think will. These are the strain meter data, which are recorded at a variety of sample rates. And I'll point out here that the first stations went in 2005, but these data, for a variety of reasons, have not been very widely used. So keep that in mind. If we now return to our scaling observations and see what does this mean for what we can observe, I've now more lightly shaded those observations which are more difficult to observe, for which the data don't provide a lot of constraint. Well, as I noted, the GPS data at high sample rates are not readily available. Typically, GPS data are available at a sample rate of 1 day. So anything durations shorter than that are really, we're somewhat blind to. Typically, in addition, time series that are longer than a number of years are also largely missing from our view. These I've left visible because this is the realm of the seismic data. So what we see is that we have two large gaps in this observational field. Another thing that affects what we can and can't observe is the noise in the earth and what our instruments can actually see. This is an analysis really borrowed from Duncan Agnew in the course he offers at UNAVCO, in which he basically formulated it like this. This is the displacement that we record at a given location by an instrument. And there's a near field term and a far field term. If this is the seismic moment and the distance, if we assume we have a rupture duration of T sub s, we can simplify that. And we see that the displacement depends on the moment, the rupture duration, and the distance. Well, we make the assumption that our detection capability is based on the signal to noise. To see something, we need a signal to noise roughly greater than a factor of 1. We have to be above the noise level. This is a standard measure of the signal to noise ratio. We typically measure the noise in the spectral domain as a function of frequency. We can estimate what that is at an RMS level over some duration, T sub s, which is what we're interested in, and convert these noise measurements into a threshold by saying our observations have to at least equal the noise level in terms of a duration. So we're going to look at that. We have lots of samples of noise, so we can estimate that threshold from the measured noise. This is an example of the laser strain meter noise and of a horizontal seismometer. Well, first let's look at the GPS, what we can see using GPS. And remember, this is a function of distance. So if we're at, and I've plotted 3 threshold curves here for 100 kilometers to 5 kilometers. So basically, anything to the left of these curves is invisible to GPS. And And so we can see that we're really only looking at things in this domain, and if we're only to here if we're really close. Well, as we add more observations, and these are all taken from the literature, and these are predominantly GPS observations, or almost all, these are all GPS observations. One of the things, as I mentioned, we're really limited. Most of these come from deep slip below the seismogenic zone, so we're really stuck looking on this side of the detection threshold, which is what the observations suggest. So a lot of this picture is colored by what we can observe. I've also added on this, these purple observations here are from Cascadia, and what we have for those are the coupled seismic observations, and these are aggregate moments of the tremor associated with each slip event. These are much easier observations to make, and it's now standard practice to say when we have tremor, these are really proxies for slow slip. And for these, and what the other thing of note is that the moment of these is much smaller than the aseismic moment, suggesting that it's the aseismic slip that's driving the seismic component. Well, we can add more coupled observations of aseismic slip, and they're coupled their seismic counterparts. So we can look at foreshocks and the precursory slip, aftershocks and afterslips, and swarmed, and places where we actually have measurements of the aseismic slip that accompanies them. And in all cases, the seismic component is much, much smaller, suggesting that it really can be used as a proxy, potentially, for when we have a seismic slip. And I'll return to that, why that's important in a minute. But what you can see is that really where our observations are beginning to cluster are largely governed by what we can observe and only fill out this quadrant. Well, for completeness, I've added now the detection threshold curves that we would calculate from the seismic noise spectra for both a broadband seismometer and an accelerometer here. The dashed lines are accounting for decreased radiation efficiency for slow events. And again, these are the measurements from the Ide et al. Original scaling. As we add more measurements now, we see that these thresholds are pretty good predictors, even given their simplicity. We can improve our detectability by playing stacking games, and that's where these measurements come from stacks. These are called very low frequency events here. But what this suggests is that we do have potentially a real gap for which we should be able to observe events in this domain here, but we don't see any. And finally, we look at what the strain meter data offer us, and those are shown here. And this suggests that these strain meter data really could fill in this critical gap in here for which the GPS and the seismic data don't permit us to observe. And to do that, so the next part of the talk is the beginnings of our exploration to look at, can these data, the high rate GPS data and the strain meter data, really fill in these needed gaps? Well, as I mentioned, looking at deep, slow slip, it really limits us to very large events, greater than magnitude about 6. The ones that offer the greatest potential to find evidence of slow aseismic slip events are swarms, largely because they're shallow and therefore close to where we can make observations. So what we've done is looked at 2 swarms, or started by looking at 2 swarms, this Brawley swarm that we're going to look at high rate GPS, and this swarm in Southern California here, where we have strain meter data at both at high rate. This Brawley swarm was studied by Gang and others, reported in this article here. And it was observed on a series of high-rate GPS stations here. And I should point out these high-rate data are post-processed in using the sort of latest, greatest analysis to do that processing. These were done at most of the stations just for the earthquakes, as is typically done. However, at this one station, P506 here, about 8 kilometers away, they actually processed 5 days' worth of data, and those are shown here. So the swarm started on the 26th of August here, and we have 3 days of data. This is 1 day here. This is one of the components of the GPS. And the reason, what you can see is that there's some coherent noise that seems to repeat on a daily basis. This is very typical of GPS data, and what's done is called, to remove that is called sidereal filtering. Basically, you stack it. This is the stack here, and remove that. The result of that stack-corrected data shown here, you can see we've reduced some of the high-frequency noise, but there's still a lot of long-period incoherent noise that I think we have to live with. And this is an amplitude of about 5 centimeters here. So this is fairly large amplitude. Well, we asked, can we see any aseismic transients in these data related that possibly correlate to the onset of the swarm? Fortunately, at this site, there's a co-located seismic station. So the red line here is just the envelope of the seismic energy at the same location. Anybody can guess, this is the start of the swarm here. And while there's a lot of structure in these GPS data, with only a single station, one would be very hard-pressed to make anything out of any of this variability. So the message is we really need these high-rate data processed and looked at as network data to be able to make sense out of given these noise levels. And finally, we look at the high-rate strain data, and these are recorded as high as 20 hertz. So we're going to look at this event here, and as with the lesson here from the Brawley data, so we really need to look at these on a network. So this is the location of that swarm. All these swarms, this is an analysis by Zialpin and Benzayan. The swarm is located here, and we have observations, 20 hertz strain meter data at these 3 stations. This station was not operational at the time. And what I'm going to show you, this was a big surprise to me. Some of the things that when you start exploring, you find things you don't expect. But what these strain meter data have, before I get to that, I'll point out that one of the problems or challenges of using the strain meters is they're so sensitive, they record everything, or a lot of things you're not interested in. These are 5-minute sampled strain meter data showing you all the deterministic noise, if you like, that they respond to. For example, the barometric pressure and the tides. They have a huge, you have to really correct for these. Fortunately, UNAVCO provides these time series, and we've simply used these to correct the 20 hertz data, being lazy, basically. If we do that, these are now, we've looked at a week's worth of data surrounding the swarm. The first thing I noticed was how amazing, with what amazing fidelity the strain meters actually record the earthquakes. These are the 3 horizontal strain components that the strain meters record. They're corrected for the barometric pressure and tides at the 3 stations. And this, so going from a distance of 23 kilometers to almost 90. This is a magnitude 4.4 earthquake. If we low-pass filter this, what we see very clearly is the static offset, not just the dynamic wave field, but the static offset. So this offers the possibility to do source studies for much smaller earthquakes. We don't need to wait for the very large earthquakes to look at the complete deformation field and look at a whole variety of scaling questions. Finally, we ask, can we see aseismic transients in these data, these high-rate strain data? And I don't have a complete answer yet, but our first look at this, and this is just a qualitative look, suggests that yes, we might. The black line are the 20 hertz data corrected again for the barometric pressure and tides. This is 200 seconds across here, and then low pass filter at a period of about 30 seconds. And what you can see, and again, the 3 stations for the 3 components. And what you can see is that we do see at the 3 sites a coherent transient with a duration of several hundred seconds. So this is really out of the range of most seismometers. This is a very small amplitude signal, but suggests that with more sophisticated detection capabilities, we can see some of these slow transients that were out of our realm before. And finally, I'm going to conclude with some examples of more pragmatic applications of these data, and that is to earthquake early warning. This is from a paper just published by Sarah Minson and others, in which she's used the high-rate GPS data. And these are the sort of low-quality data. They're processed basically in near real time. And just a schematic of how the algorithm works. You know that there's an earthquake has occurred from the seismic data. You look at the data in the P-wave range and measure the static offset. So these are the various versions of a smoothed GPS time series, because all you're really interested in is what the static offset is. And that's measured here. Those are then fed into a Bayesian inversion in which you look at the probability. You not only solve for the moment, but the strike, dip, and slip distribution for every possible orientation. That probability, the strike and dip, those probabilities are shown here. You pick the slip distribution that goes with the most probable strike and orientation and report that. This gets updated every second as new GPS data come in. To illustrate that more schematically, this is for the Tohoku earthquake. This is what the inversion produces after 60 seconds, the probabilities of the strikes and dips, and the fault plane that goes with that, and the slip. The earthquake is still evolving. It's not yet reached its full magnitude. After 2 minutes, the magnitude estimate is getting to be quite robust, but the fault orientation estimate is still varying quite a bit. And after 3 minutes, we have both a robust estimate, a very robust estimate of the moment, and a relatively good estimate of the fault geometry and slip distribution. And finally, another observation, and I think another approach to early warning makes use of both seismic data and geodetic data simultaneously and sort of gets the best of both. I think this is really a direction that monitoring needs to go. At the sites, this is a work of Gang and others. We have both an accelerometer and a high-rate GPS stations. They're co-located. Shown at the top, again, this is a magnitude. This is a small earthquake. We have the accelerometer data, acceleration shown at the top. The high-rate GPS data is shown in the gray, and you can see that it's very noisy. By combining these two data streams using a Kalman filter techniques, we can estimate very robustly the velocity field as well as the displacements, much better than we could with either data set independently. So to conclude, I would say that we really have only begun to explore what we can do with these high-rate GPS data or geodetic data, and that we really need to make a bigger investment in ways in exploring how we can use them more effectively. And I think one of the great lessons of IRIS has taught us that if you make data readily available and usable, even to seismologists, they will get used and we will make new discoveries. And I'll leave it at that. Thank you.